we can work on it. But the open, what can you do? There's not much you can do, right? So, in real life, if you want to do an open, suppose someone wants to do an open. Obviously, that's an issue there. So what do? Since I can make a good short, why don't I get the open from here? So, in real life, if you'd like to design a short circuit, yeah, we can do that. If you want to design an open, what we do is we design a short, lambda by 2 away, lambda by 4 away. So what we do is we go to make a good short, lambda by 4, and I have an open circuit. So that's the open circuit that you would implement. If you need to design an open circuit in your transmission media, you do a short. So in waveguides, here's the waveguide section. I want to do an open here. What we do is we hook up a lambda by 4 section and make that a short. Same thing as in transmission line. So when you go to the lab and you do a calibration to a network analyzer, one of the types of calibration that we make is we do an open short load, right? OSL, or sometimes OSR, open short load. So we go to the port and connect a short and make a measurement. We connect a 50 ohm load and make a measurement. We connect an open circuit load, you will be surprised, there is an open circuit load. And what is it? It's just like a short cavity that is designed to minimize the radiation, and that is calculated. The impedance of that section here is calculated and entered into your machine calculation, so it will correct for the errors because it's not exactly a ohm, right? So that is just, so anyway, this idea here brings out something else. This lambda by 4 thing here. So let's talk about the properties of a lambda by 4 section and a lambda by 2 section. These are two special lines that we always like to study. Our expression is still there, and we're talking lossless. Lossless means J beta. So I'm going to take the H out, and make that J beta, J beta. The J is inside the tangent, but it comes out here, okay? So take the gamma out. And let's do two special cases. D is equal to n lambda over 2, multiples of lambda over 2. Half wavelength, or a wavelength, or 3 halves, or what have you. Z of n lambda over 2 line, input, is equal to, put that lambda over 2, that becomes what? It's 2 pi over lambda, lambda over 2, that's a pi, tangent of pi is 0, Z naught, times ZL over Z naught, which gives ZL. So if you have a line, n lambda over 2, and you have a ZL, what you see here is ZL. The line characteristic impedance is Z naught. Let's take some numbers. 50 ohm line, I'll put 75 ohm load here. I see a 75 ohm here. See the same exact impedance value. I'll put an inductor here, JX, I see the same exact JX there. Nothing changes. That kind of phenomena here, or that kind of property, is very useful in designing special lines that are kind of odd. You know, I'm going into a transmission line here, let's say 75 ohm line, and 75 ohm line there. And I have to design a section here that will go through maybe a wall or a bend or something, you know, something that will be weird, okay? The line here is going to be crooked, and I can never control its impedance, all right? Or I end up with some value that I don't really like. Or what you need to do is just make that an inland over 2 and you are free. We'll see that in waveguides. You have a waveguide that's going this way, and you have to make a bend, right? So that's your Z0 here, Z0 there, and this may be a Z1. So we make the bend length N-land over 2, and we maintain or retain our impedance again. Sometimes we have to do a twist, like this waveguide going this way, and then we have to connect the waveguide going that way. All right? So you need to design a twist. You make the length of that. That twist is, again, an odd number thing, so you do the same thing. Or you have some connectors, what have you. See, that's what you do. That's the lambda over 2 line. The lambda over 4 line is different. Let's say D is equal to odd lambda over 4 multiples. Obviously, the even will go there, right? Even multiples will get you here. So I'm talking here odd multiples. I wrote this in a funny way. Odd multiples of lambda over 4. All right. So in this case here, beta D is 2 pi over lambda times lambda over 4, or odd multiples of that. That gives you a pi over 2. Multiples of pi over 2 times, let's say here, m odd. That's your multiple. The tangent of pi over 2, we know that goes to infinity, plus or minus infinity. Right? So the tangent blows up. That means this quantity here is small compared to that. And this quantity here is small compared to that. The tangent beta D goes with the tangent beta D, and you end up with Z0 squared over ZL. So what happens? Here's a section of line, M odd times lambda by 4. And let's say we connect 100 ohm here, and that's a 50 ohm. What do I see here? Anyone says 25? Okay. Let's say I put a J10 here, and that's 50 ohms. What do I see here? 2500 by 10, that's 250, minus J, 250, right? So I have an inductor here, I saw a capacitor there. Well, we saw a minute ago that when we had a 0 here, we saw an open circuit, same thing. When I had an open circuit here, I see a 0 there, short circuit. It's an inverse situation. Do we have applications for that? Absolutely. Lots of applications, especially in matching. All right? If this is what you have here, suppose I want to match a situation where I have 50 ohm, I have a 100 ohm load, and let's say a 25 ohm source. So what do is I choose a lambda by 4 section, and I choose its impedance to be the square root of the product of these two, and I'm done. Okay? You will see that eventually in waveguides. Here's a waveguide that you have a load and you have a source, and they are not matched, so I come up here with a section. And if it's the same dimensions, obviously it's the same characteristic impedance, so I do fill it with different dielectric. I put some dielectric here such that Z naught here is equal to the square root of Z source times Z load, and I'm done. And we'll actually, when we get there, we'll have some practice on doing this kind of thing. So we call that lambda by 4 matching section. It's a transformer. When you think about it, this is a 1-to-1 transformer. Impedance is the same. This one here is an inverse transformer. Right? It's not a direct relationship, it's given by that. It's an impedance transformer. Now, any section of line is an impedance transformer. But these particular two are straightforward expressions that have lots of applications. Next time when we try to do matching, we will select the section of line to get us the impedance that we want, right, for a particular matching characteristics. We are done. Thank you very much. Any questions before we go? Okay. Lab tomorrow evening, and I believe Kareem sent you links to everything. He created the scholar site, and we'll see you at 6:15 or 6:30, I forgot. 6:15? 6:30? 6:30? Yeah. Yeah, I believe the earlier class ends at 6:15, so 6:30, yeah. The lab is on the 6th floor, the radio lab on the western side of the building.
It's 6th floor radiation lab.
Radio lab, radio engineering lab. It's 617, I believe. 613? 617 or 619, because my lab was next to it, and 618 was my lab. 617, I believe. 617. 619? The other side? 619.
Maybe I filled out the dual thing wrong, but I have a lab at the same time. I don't know how that ended up. I must have screwed up somehow.
Well,